I've done sort of an overview of all three of the Newton's laws as a sort of a refresher, and now we're going to delve a little bit deeper into each one individually. And I'll do Newton's law first law. Tomorrow I'll jump to the third law, and then I'm going to jump to the second law, and that's because the second law is the one where there's some formulas and stuff, and that leads into the second part of the unit, which is the word problems. More word problems. Okay. So today we're going to do things a little bit backwards. There's about, 12 or 14 questions there, something like that. So you can do those with someone if you want, discuss them however you want. I'll give you about maybe 30 minutes or so roughly to complete those, and then we'll go through and we'll see how we did. You guys don't have one because I missed you. And in the meantime, I'm going to hand something else out as well. So you got some time. I'm going to start the clicker should be turned on so you can sign in. If you're having trouble with clickers, grab another one, and I will start the assessment, and then you can go. Alrighty, so number 1 says, stay with me here, you've had lots of time to visit, so here's where you actually do the learning part. How'd you do? 30%. Oh. Alright, well, let's do the learning part here. So, imagine a place in the cosmos far from all gravitational and frictional forces, frictional influences. Suppose that you visit that place. Of course, I'd have to fill out way too much paperwork for you guys to go there. And throw a rock. The rock will gradually stop or continue in motion in the same direction at a constant speed. And the answer is, of course, B. Because Newton's first law says, objects in motion stay in motion. So once you throw it, it keeps going on forever. There's no gravity. There's no friction to slow it down. Now, this brings me to number 2. Here's where I really test to see if you get it. A 2 kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed and in this direction? No decimal place is needed. And the answer, we'll see how many people got it, is 0. 0 newtons. Who said 0? Some people did, it looks like. Why is it 0? Because objects in motion stay in motion. You don't need a force to keep things going. How come then when I want to push my binder across the table, I have to keep pushing it? Why does it not just keep going? Because of friction. Right? And that's why I had to throw this little word in. How much net force is required? So if the friction force is, say, 3 newtons, then I got to push with another 3 newtons, and the net force is a big fat 0. 0 newtons of force is required to keep the object moving. I'm warning you right now, that question will be on the test in some form or another. It won't be worded like that, but it's the same question. Do you understand what it means by objects in motion stay in motion? It means you don't need a force to keep things moving. Okay, Mac and Tosh are arguing in the cafeteria. Max says that if he flings the jello with a greater speed, don't do that by the way, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with and explain why? Well, the correct answer is B, Tosh. Okay? Inertia only depends on mass, right? Objects at rest stay at rest, and that's based on their inertia. The bigger the object, the more inertia it has. The bigger the object, the bigger the mass has, or the bigger the object has mass, the greater inertia. If you think about a train trying to stop, how easy is it for a train to stop? It takes a long time. It's got a lot of inertia, okay? What you're thinking of when we deal with speed, right? If you've got mass and speed, what you're thinking of is something else called momentum, which is a grade 12 topic. Okay, but inertia is just an object's tendency to keep on doing what it's doing, and that is only dependent upon mass. Okay, supposing you were in a space in a weightless environment, would it require a force to set an object in motion? Keep in mind, objects in motion stay in motion, objects at rest stay at rest. Would it require a force to set an object in motion? And the answer is, well, you probably know because you either got it right or wrong. The answer is yes. But Mr. Bennett, you just said objects in motion stay in motion. I know, I also said objects at rest stay at rest, unless you apply a force. Suppose you're in space and weight is matter. Would it require forces that are not in motion? Yes, it would. If I have my deck of cards up there in space, if I was up on the old space station and I let my deck of cards go, what would happen? It would just hover there right in front of me, would it not? Just would stay right there. You see video of this all the time. Right? The only way to get it to move is to give it a push. Right? If I have time, I'll show you a video of that. Fred spends most Sunday afternoons at rest on the sofa watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? Well, because he's sitting there not getting exercise, eating a lot of chips, it's going to increase his inertia. Increase. He's going to get bigger and have more inertia.
So if like someone weighs more than you, they have higher inertia.
It's harder to get them stopped, or it's harder to get them moving, right? Think about the big running backs, right? That have a lot of mass. They're hard to bring down because they have a lot of inertia. They have a lot of momentum as well. Ben Too Close is being chased through the woods by a bull moose, which he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, yet if Ben makes a zigzag pattern through the woods, he'll be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. So, is it? Well, the answer is there. The answer is B. Right? The moose has more mass, so he has more inertia, not able to make zigzags as easy. Right? If you're small, you can go left to right. You can change your direction quite quickly. It requires a small force. The big moose can't do that, right? It's no different than the little running back trying to get brought down by the big linebacker. Right? The little running back's quick, can move left to right, change direction quite easily, requires a small force. Linebackers can't do that. Think about the Titanic. They saw the iceberg. They tried to avoid it. How come they couldn't? Because they're giant. Giant, big ship requires a lot of force to move that change in direction, that acceleration. Remember, big masses require big forces. Two bricks are resting on the edge of a table. This is a lot of reading. Surely she's short. Thank you. I didn't write them. I just admired them. Stands on her toes and spots the two bricks. She acquires an intense desire to know which of the two bricks are most massive. Since Shirley is vertically challenged, that's code for short, she is unable to reach high enough and lift the brick. She can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the two bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusion? So how can she figure out which one is the bigger one? The brick that moves more has more inertia and is heavier. The brick that moves the brick that moves more has less inertia and is lighter. Both bricks feel the same and move the same distance. Well, of course, the answer is B. The brick that moves more has less inertia and is lighter. If I've got two cards that are identical, right? But one is more massive than the other, I'm going to stick a weight on. Which one's going, if I push them at the same speed, can you just slide over everything else? If I'm going to push them at the same speed, which one's going to go farther? I didn't push them at the same speed. Let's do it. They're on wheels, so they're kind of frictionless. Clearly my left arm is stronger than my right arm. It's hard to push them at the same. This is the worst demonstration ever. You laugh at me? I'll show those cards. Jason, come and sit on this one, would you? There we go. See? It's not a fat joke. Any size person would be fine. Okay, well, let's see if this one, you like this one? You like that cat? It makes you miss your cat, Anna. Did you have a big fat cat? Yeah. Okay, so the guy's name is, did you catch it? Look out below? I didn't write it. Look out below drops an approximately 5 kilogram fat cat of approximate weight 50 newtons off the roof of his house into the swimming pool below. Now, before I go any further, this is a fictional cat. No actual cats were harmed in the making of this question. Upon encountering the pool, the cat encounters a 50 Newton upward resistant force, assumed to be constant. Use this description to answer the following questions. So, how much does the cat weigh? 50 newtons down, right? Gravity. When he hits the water, 50 newtons up of water resistance, right? Okay, so which of the velocity time graphs best describes the motion of the cat? Is it A, B, or C? How many people got it right? Because the answer is B. Not that many. Why is it B? Are you stop? Does the cat stop?
No, it's the constant velocity.
That's correct. So, as the cat falls, his velocity, we'll assume it's a male cat, I guess. The cat's velocity increases. Why is it below zero? Because he's falling in the negative direction. Wait, why are you showing him what you got in your clicker? Oh, well, here's the learning part where you're going to figure out how to get it right. So it's falling negatively, so it has a negative speed, and it's increasing in speed. But once it hits the water, as Tia pointed out, both of those forces are now what? Equal. What's the net force? Zero. So if the net force is zero, then objects in motion stay in motion. So it keeps falling, but at the same speed. And the same speed is shown by a flat line. So this cat is going to hit the water and then keep going at the same speed to the bottom of the pool. Don't worry, Luke jumped in and saved the cat. It's a happy story, except, well, probably the cat's not very happy with this whole thing. Doesn't necessarily have to be a cat, could be any object. Which of the following dot diagrams best describes the motion of the falling cat? From the time that they drop to the time they hit the bottom of the pool, the arrows on the diagram represent the point at which the cat hits the water. Support your answer with sound reasoning. So, now that we know it's constant velocity, which one of those is correct? And I probably should make this a little bit bigger, eh? Yeah, it's pretty tough for you to see, I agree. Okay, so constant speed, that's when the dots are the same distance apart. So which one is that? It looks like A. The answer is A. Way to explain it. Once the cat hits the water, the forces are balanced, the cat will stop. That is, of course, we now know, false. Which part of that statement is false? The cat will stop part. Are the forces balanced? That is true. Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. False. Right? Why? Because the forces are balanced. The net force is zero, so that means that the acceleration is also zero. The cat's speed stops changing because the acceleration is equal to zero. If you want to write that down, you can. Okay, but that's important. The forces are balanced. If the net force is zero, then the acceleration is zero. I'll pause for a second because it's... Okay, is there one more question? Two more. Upon hitting the water, the cat will bounce upwards due to the upwards force. Also false. Why? Net force is zero. If the net force is zero, objects in motion stay in motion. Why do I have to keep repeating it? Because kids don't believe me. Or they don't believe what it means. They can say it. Okay, here's the number one thing you need to learn from today. If the forces acting upon an object are balanced, then the object A must not be moving, must be moving with a constant velocity, must not be accelerating, or none of these. And what is the right answer? C, must not be accelerating. Because balanced forces Balanced forces means F net is 0, and if F net is 0, then that means that acceleration is 0. Right? The net force is 0, the acceleration must not be accelerating. It's either at rest or it's moving at a constant speed.
So what's the difference between it must have an acceleration and it must move at a constant speed?
It says it absolutely, it could be at rest. If something's at rest, it's not accelerating either. I guess everybody's saying that 0 is a constant. That's good enough? That's better. Okay, that is all I have.